Cosmic matter mystery. The beginning of everything was a paradox. In the first searing moments of the universe, less than a second after the Big Bang, the cosmos was a roiling, incandescent soup of pure energy. From this energy, particles were born. But physics, in its most fundamental and elegant form, demands balance. It demands symmetry. For every single particle of matter forged in that cosmic furnace, an equal and opposite particle of antimatter should have been created. Think of it as a perfect cosmic accounting system. For every electron, a positron. For every quark, an antiquark. A perfect one-to-one pairing. This isn't just a neat theory, it's a cornerstone of our understanding of reality. Matter and antimatter are twins with opposite charges. When they meet, they don't just cancel out, they annihilate. They vanish in a flash of pure energy, returning to the state from which they came. Imagine that primordial universe, a frantic, chaotic dance of creation and annihilation. A particle of matter is born, and for a fleeting instant it exists. But its antimatter twin is never far away. They find each other in the dense, hot plasma and are instantly erased from existence. Their combined mass converted back into a burst of gamma-ray photons, pure light. This process would have happened trillions upon trillions of times, everywhere, all at once. The universe would have been the most spectacular and the shortest fireworks display in history. As the cosmos expanded and cooled, this frenzy of creation and annihilation would have slowed, and eventually it would have stopped. And what would be left? Nothing. Or more precisely, nothing. The matter and antimatter, having been created in perfect balance, would have wiped each other out completely. The universe would be a vast, empty, and sterile place, filled with a uniform, lukewarm sea of radiation, the leftover energy from all that annihilation. There would be no stars, because stars are made of matter. No galaxies, because galaxies are collections of stars. No planets, no asteroids, no dust clouds, and most certainly, no us. But you are here. You are reading this, breathing, thinking. You are made of matter. The device you're watching this on, the chair you're sitting in, the planet beneath your feet, it's all matter. So, what went wrong? Or perhaps, what went? This is the most profound mystery in all of cosmology, a puzzle so deep it challenges the very notion of our existence. It's what we might call physics's original sin, a fundamental crime against the laws of symmetry. Somewhere in that first fraction of a second, the perfect balance was broken. The scales of creation, which should have been perfectly level, were inexplicably tipped. The universe committed a terrifying glitch. The evidence tells us that for every billion pairs of matter and antimatter particles that annihilated each other, a single solitary matter particle was left over. Just 1 in a billion. It doesn't sound like much, does it? A rounding error in the cosmic budget. But that tiny, almost infinitesimal imbalance, that leftover scrap, is everything. Every atom in your body, every star in the night sky, every galaxy in the observable universe is made from that 1 in a billion survivor. We are the descendants of a cosmic anomaly. Our existence is predicated on a fundamental flaw in the fabric of reality. If the universe had followed its own rules perfectly, it would be a featureless void of light. Instead, it is filled with the intricate, complex, and beautiful structures we see today. This isn't just a curious little problem for physicists to ponder, it is the central question of our being. It forces us to confront a terrifying possibility, that our universe, in all its grandeur, is an accident, a fluke, the result of a glitch in the cosmic operating system that allowed something to persist where there should have been nothing. This is the Baryon asymmetry problem, and it is the shadow that looms over everything we think we know about creation. Why is there something rather than nothing? The answer, it seems, is that the universe cheated. And now, scientists are on the hunt, searching for the clues left behind by this cosmic crime, trying to understand the nature of the glitch that allowed us to exist. Quantum glitch theory. So, how does a universe cheat its own laws? How does it break the most fundamental symmetry of all to conjure a cosmos out of a statistical error? In 1967, the brilliant Soviet physicist Andrei Sakharov laid out the blueprint for this cosmic heist. He proposed that for matter to win its war against antimatter, three specific conditions had to be met in the early universe. These are now known as the Sakharov conditions, and they form the foundation of our search for the terrifying glitch. First, you need a process that violates something called baryon number. Baryons are a family of particles that includes the protons and neutrons that make up the atoms in your body. In our everyday world, baryon number is always conserved. You can't just create or destroy a proton out of thin air. But to get an excess of them, there must have been some exotic, high-energy process in the early universe where this rule was temporarily broken. Second, and this is the absolute heart of the glitch, the universe must violate something called CP symmetry. Let's break that down. C symmetry, or charge conjugation symmetry, suggests that if you take a physical process and swap all the particles with their corresponding antiparticles, the process should behave in exactly the same way. P symmetry, or parity symmetry, says that a process should look the same if you view it in a mirror. CP symmetry is the combination of the two. For a long time, physicists believed CP symmetry was an unbreakable law. But in 1964, an experiment revealed that the weak nuclear force, the force responsible for radioactive decay, does in fact violate CP symmetry, just a tiny bit. It was a shocking discovery. The laws of physics are not perfectly ambidextrous. This means that matter and antimatter are not perfect mirror images of each other. There are subtle differences in how they behave and decay. This was the first clue that a glitch was not only possible, but actually written into the laws of nature. The third and final condition is that these processes must have occurred out of thermal equilibrium. Imagine a pot of water in perfect equilibrium. The temperature is the same everywhere. Chemical reactions happen in both forward and reverse directions at the same rate, so nothing really changes overall. The early universe, however, was violently out of equilibrium. It was expanding and cooling at an unimaginable rate. This rapid change meant that any imbalance created by the first two conditions could be frozen in before the universe had a chance to smooth things out and restore the balance. The Big Bang itself provided the perfect chaotic environment for the crime to take place. With Sakharov's conditions as our guide, physicists have developed several compelling theories. One of the most elegant and promising is called leptogenesis. This theory suggests the original sin wasn't committed by the baryons, but by their lighter, more elusive cousins, the leptons, a family that includes electrons and the ghost-like neutrinos. In the furnace of the early universe, this theory posits the existence of extremely heavy hypothetical neutrinos. As these massive neutrinos decayed, the known violation of CP symmetry kicked in, causing them to decay slightly more often into matter leptons than antimatter leptons. This created a secret, hidden imbalance in the neutrino sector. Later, through a bizarre but accepted quantum process, this lepton imbalance was converted into the baryon imbalance we see today. The matter that makes up stars and galaxies is essentially a second-hand echo of an ancient asymmetry among the most ethereal particles in the cosmos. Scientists are actively hunting for evidence to support these ideas. At CERN, the LHCb experiment is meticulously studying the decay of exotic particles, searching for new sources of CP violation beyond what our current theories predict. Meanwhile, incredible experiments like T2K in Japan and the upcoming DUNE experiment in the United States are studying neutrinos with breathtaking precision. They are looking to see if neutrinos and their antimatter counterparts, antineutrinos, oscillate or change their type at different rates. Finding such a difference would be monumental, a smoking gun pointing directly towards leptogenesis as the origin of all matter. In the end, our existence seems to be the beautiful, complex, and profound consequence of an imperfection. We are not the product of a perfect symmetrical creation, but the result of a flaw, a crack in the mirror of reality. That 1 in a billion rounding error, that terrifying glitch in the cosmic code, is the reason we are here to wonder about it at all.